In determining whether a given permutation is an even or an odd permutation, we are going to anchor this idea on the number of transpositions that were used to solve or to determine, or that will result to the same permutation here. Now, these three permutations are already part of the previous videos. We were able to determine the expression for each of these permutation as a result of a product of disjoint cycles. At the same time, we also determined their expressions as a product of transpositions. And this time, we just simply need to count the number of transpositions for each permutation here and decide whether it's an even or odd permutation. Now, I'm just going to copy here the direct answers from the separate videos. So this might be a shorter version of our video instruction. So you might want to review the previous videos in determining the expressions as product of transpositions, or even as product of disjoint cycles to which the transpositions were taken from. So our first permutation, we have here this is actually the result. If we are going to multiply the following transpositions, 1, 8, you will have 3, 4, 3, 6, 5, and 7. If you would like to verify, you could always try doing it like this. 1 is mapped to 1, 1 is mapped to 1, 1 is mapped to 1, 1 is mapped to 8. Okay, that's here. Then for 8, 8 is also mapped to 1, right? For 2, since there's no 2 here, 2 is mapped to 2. For 3, 3 is mapped to 6. And since there's no 6 here, so 3 is mapped to 6. For 4, so you have here 4 is mapped to 3. 5 is mapped to 7. For 6, 6 is mapped to 3. But when you go here, because you're going from your right to left, so again, 6 is mapped to 3, but 3 is mapped to 4, so that 6 is mapped to 4. 7 is mapped to 5. And then, of course, again, as mentioned, 8 is mapped to 1. That's already correct and pertaining to the identified product of transpositions, rather. Now, looking into this result, we see that there are 4 transpositions for the first permutation. We have to multiply 4 different transpositions. We have 1, 8, 3, 4, 3, 6, and 5, 7 to get the result which is similar to the first permutation. Since this is an even number, this would mean that our first permutation is an even permutation, because the number of transpositions will determine the type of permutation. So if we have even number of transpositions, so our permutation is an even permutation. If it is odd, automatically our permutation is also an odd permutation. Now let's proceed to the second. The second here, in the previous video, this could be expressed as this product of transpositions. 1, 4, 1, 3, 2, 6, 5, 7, and 5, 8. As you can see, there are 5 transpositions here. This would mean automatically that this permutation here is rather an odd permutation. If you like to verify again, you can do it like this. 1 is mapped to 3 here, so that's correct. 2 is mapped to 6. 3 is mapped to 1, but 1 is mapped to 4, so 3 mapped to 4. 4 is mapped to 1. 5 is mapped to 8. 6 is mapped to 2. 7 is mapped to 5. 8 is mapped to 5, but then 5 is mapped to 7. Okay, so that's correct. It returns to our given permutation. Our last permutation here has been identified already as a cycle, because we only have one orbit containing actually all the elements, and it contains more than one element. That's why it's considered to be a cycle, and from that cycle alone, we're able to come up with this product of transpositions. You have 1, 2, 1, 5, 1, 6, 1, 8, 1, 7, 1, 4, and 1, 3. Again, you might want to review our previous video for this. So you have 1, 2, 3, 4, 5, 6, and 7. That's 7 transpositions. With this in mind, we are now sure that this last permutation is identified or classified as an odd permutation as well. Okay? Because it has odd number of transpositions. So again, if you would like to verify, 1 is mapped to 3, so that's correct. 2, how about 2? 2 is here, 2 is mapped to 1. For 3, 3 is mapped to 1, but here 1 is mapped to 4. That's why it's 3 mapped to 4. For 4, 4 is mapped to 1, but 1 is mapped to 7. Then for 5, 5 is mapped to 1, but 1 is mapped to 2. 6, 6 is mapped to 1, 1 is mapped to 5. We don't need to return to 1 because 1 is already mapped to 5 here, so 6 is mapped to 5. 7 is mapped to 1, 1 is mapped to 8. And finally, 8 is mapped to 1, 1 is mapped to 6. So these are the results in determining, or this is the process in determining whether a permutation is an even or an odd permutation. It anchors to the number of transpositions that were multiplied to solve for the given permutation. So basically, it's being connected. The idea of orbits, the idea of cycle, the idea of disjoint cycles, transpositions, and the identification of even and odd permutation. Thank you very much for watching.